Our last lecture today is Umut Varolgunes from University. It's a talk about hacking keating.
Yes, I think I will. But okay, so in the last lecture, I kind of got to a much earlier. I stopped at a much earlier point than I had, intended to a month ago. But okay, so I'll try to still get to this theorem. Okay, so the last time what I explained was essentially I kind of explained what a Kähler structure on a complex manifold is and how to obtain examples of that. So if there is one more thing I kind of have to start talking about Looijenga conjectures and the kind of their symplectic geometry and SYZ fibrations and so on. It's Kähler structures on toric varieties. And I will not say anything complete at all. I will just say, so if you have a Y, which is a projective toric complex projective, toric smooth variety, you can get from this, and let's also just say it's 2D, so it's a surface, okay, just for just because that's the case that we're going to be interested in later on. To this, you can associate a polygon, a convex polygon inside R2. Is the sound still coming?
From here, yes.
Yes? Okay, so to each Y, which is a complex projective variety, you can associate some a polygon, a convex polygon. So this is convex, and it's rational, which means that the slopes of its sides are rational. And also, we have the condition that if you take the primitive integral generators at each of these corners, then they span the integer lattice at this point. Okay, so this kind of thing is called the Dalzan polytope, and they encode kind of the symplectic geometry of this projective toric variety. And one thing that I want to say is that instead of trying to define this polytope, I just want to say I want to make a connection between this toric variety and this polytope by saying that there actually is a map between them. So I take Y2 and I equip it with some Kähler form. And I should also say that kind of we know that there's not going to be a unique Kähler form on Y2 or a Kähler class, but you can kind of realize different Kähler classes by changing this polygon, kind of moving its edges without changing the type of the polygon. So you can take something like this, for example. You can add this bit where these two are parallel. This would correspond to a different Kähler structure on this projective variety. Okay, so this kind of size of this polygon tells you something about the Kähler structure that you chose on your toric variety. So, there is some connection between exactly which kind of size polygon that I choose and which Kähler class I choose on my projective toric variety. So for some choice, okay, so there exists a map from this Y2 to this polygon, and let's call it pi. This is called the moment map. Okay, it's the most kind of important example of a Lagrangian torus fibration, I think. So what does it mean? So Lagrangian, recall that L inside some symplectic manifold M omega is called Lagrangian if it's half-dimensional and the symplectic form restricted to L vanishes. If you take any two vectors tangent to the Lagrangian, then the symplectic form pairs them to 0. So now what's happening here is that if you take a point in the interior of this polygon, then you see a full Lagrangian torus. If you take a point that lies over a point along the edge, but not on the vertex, then you see a circle. And you see, if you take a point that lies over a vertex, you see a point. Okay, so we know that because this is a toric variety, there's this toric action on it. And the vertices, the preimages of the vertices correspond to the fixed points of the toric action, the action of the torus. The ones on edges correspond to the loci where there is some part of the torus acts trivially, but some other part of the torus acts non-trivially. And lie in the C star squared inside this toric variety. Okay. Okay, so now let's start talking about Looijenga pairs. Let's say why these are Looijenga pair. Okay, so I mean, we have this kind of picture. This is Y, this is D. It's a cycle of rational curves. They have their self-intersections. And we know that there exists a holomorphic volume form on Y comma D with simple poles along D. So you can extend this holomorphic volume form to Y, but only at the expense of making it meromorphic. And the poles of this are exactly along D, and they're simple poles. Okay, so that's one thing we can do. So we automatically have a holomorphic volume form. And remember also that this holomorphic form, volume form is well defined up to multiplication by a non-zero complex number. Okay, so well defined up to, so by well defined meaning from this YD being a Looijenga pair, you immediately obtain the structure up to multiplying with a scalar. See. Okay, so that's almost a canonical choice. And another thing that we can do is we will also consider Taylor forms on Y, and we can obviously restrict these to the complement. I mean, nothing to it. One thing that I want to point out here is that if D supports an ample divisor, so there is some positive multiple, you're adding up some positive multiples of the components of this anti-canonical cycle, you can obtain an ample divisor, which means that there exists an ample line bundle which admits a section, and it only has kind of zeros along this divisor. Okay, so you don't have to know what this means. Let me just say something. So this then Y minus D is affine and admits an almost canonical, as we discussed last time, preferred symplectic structure. By almost canonical, I mean that it's unique up to symplectomorphism. Okay, and from yesterday's talk, this is what was called the positive case. Okay, so this is the opposite of the negative case, which was relevant to the Looijenga conjecture. Okay, so now maybe a theorem, and this is due to many people many people, I will just say many people. Some names are Mark Gross, Danny Aru, I think his name is Edward Goldstein, and then other people involving Yushen Lin and so on. Many people contribute to making the statement, which is actually not that difficult. If I consider this Calabi-Yau manifold, which is obtained by Y, I just removed, so I look at the interior. I want, I know that I have a holomorphic volume form there, and I consider it with its standard J, the J that it comes with. I consider one of these scalar structures that are restricted from Y, and I have this omega. Okay, so this admits YZ vibration for, I will say, for a large family of omegas. This might be kind of, it might actually cover all Kähler classes, but I don't want to say something very precise about this on Y. And so let me give an example. So this thing over the interior of the polygon, we have SYZ vibration here. Okay, special Lagrangian vibration. Special SYZ is equal to saying special Lagrangian. I'll say quickly what it meant. Okay, so we know that this toric variety is also a log Calabi-Yau pair, if I consider its toric divisor. And I know that in the complement of this divisor, if I look at the interior, I get a C star squared. And on the C star squared, I have the standard D log X, D log Y holomorphic volume form. So with respect to that, this is going to be a SYZ vibration. Okay, so now what was an SYZ vibration? So recall Lagrangian meant this. And if I also have omega, which is a holomorphic volume form, special Lagrangian means that if you look at imaginary part or imaginary part of any phase of this holomorphic volume form, then that should be 0 on this Lagrangian. Okay, so but in general, this is a very different kind of condition, at least at the first sight. But here it's not really different, right? If I have a holomorphic volume form in a two-dimensional thing, then this is just a symplectic structure, a real symplectic structure. So again, I'm just asking for this submanifold to be Lagrangian with respect to this other symplectic structure. That's what it means in this dimension, to be special Lagrangian. Means that it's a Lagrangian with respect to the Kähler form, but also with respect to some phase of the holomorphic symplectic structure. Sorry?
It has switched off for all theta.
No, there exists such a theta. Or maybe even like special, like theta special Lagrangian, let's say. Means that it's true for that theta. And this one, so what I'm going to do is, so here, convention. And I will explain this convention a little bit more carefully later. But for now, let me just say, so convention is so that if gamma is a fiber homology class, so I'm talking about this SYZ vibration that I didn't even, but there is going to be one, and it will satisfy the property that if I integrate this holomorphic volume form along a fiber, then I will just get one. Okay, and this could be some other number because I don't know, I didn't say anything about. So this I get to multiply this omega with some complex number, and the SYZ vibration can also be for some particular phase. So I multiply omega with a number so that this happens. Okay. And this is going to be a 0 special Lagrangian. Okay. Lagrangian, which means that the imaginary part of omega equals 0. Restricted to L. Okay, it's just a convention. And from now on, whenever I say special Lagrangian, it will be a 0 special Lagrangian. Just the imaginary part will be vanishing over the Lagrangian. Okay, so I'm not going to say too much about how you prove this theorem, but so sketch, just some steps. So first of all, we're going to use toric models. And this one, the vibration star. Okay. And the previous lecture, I told you that if you do blow-ups, point blow-ups along Kähler manifolds, then you can kind of construct Kähler structures on the agree with the previous Kähler structure outside of some neighborhood of the exceptional divisor. So that statement, kind of understanding of that, will produce for you the Kähler structure that you want to use here, okay, for the statement. And then, you know, you already have a canonical holomorphic volume form. So using that kind of Kähler structures and the given omega, you're going to be able to produce an SYZ fibration starting with this one and then doing some operations to this fibration. Okay, so Phil already, let me just write that. So use S1, so use local S1 symmetries and the kind of reduction picture. So the reduction picture, I have no time to get into this. It lets you construct Lagrangian fibrations by constructing Lagrangian fibrations on a lower dimensional space and then lifting them up. Impossible to explain, but you do this stuff and then you obtain an SYZ fibration over this Calabi-Yau manifold. It's not trivial, and you know, it takes some work to do it, okay? But it's true. And somehow there is an impression that this statement is complicated, very difficult, but it's also not very difficult. One thing that this doesn't have is that this is not, like this is actually what's called an almost Calabi-Yau structure. There is some extra condition on almost Calabi-Yau structures relating, so the omega to the power n should be related to the holomorphic volume form in some way. And when you impose that, this is dimension 2, not just for Looijenga pairs. I think it's just, it's like yesterday it was attributed to a paper from 2021, and this is not really true. Okay. Okay, but now that we have our Calabi-Yau manifold and as SYZ fibration, we can pretend that there is mirror symmetry, and we can produce a mirror taking the dual fibration and doing some complicated stuff and so on, which we actually don't know how to do, but we're going to pretend that we know how to do it and see what we get. It will give us some prediction. Okay, so SYZ duality suggests. I don't think we do, no.
There's not so many singularities.
I haven't seen it worked out.
So in the vibration, if it works in this focusing.
No, you can make it focus. No, I mean, so gross Hacking Keating or scattering diagram picture that works out, but I don't know if people wrote. Well, maybe I should, like, there are some issues with running the scattering diagram program, right? There are some convergence issues. I think in some cases it's resolved, but they don't really produce some complex mirror, but they produce some kind of formal thing. And sometimes you can actually turn it into a complex thing, but it's a difficult story. Okay, so let me just go with the imprecise versions for now. There should be a mirror such that, So the mirror will also be a Calabi-Yau manifold with a SYZ fibration, and such that the dual fibration can be identified. Okay, let me call this Lagrangian fibration, give it a name. This is pi from y complement d to, let's say, some base b. Okay, that's my special Lagrangian fibration. Should be a mirror such that the dual fibration can be identified smoothly with pi. Okay, so let me say it like this: pi omega is equal to pi. So this in higher dimensional situation, because like a dual is what they call self-dual. A torus fiber in this case is kind of automatically dual to itself because of Poincare duality. Poincare duality in this dimension gives you an isomorphism between H1 and the dual of H1 if you choose a fundamental class. So because of that reason, in this dimension, you can actually think that the dual fibration, without any of its structures, just as a smooth fibration, is the same as the fibration that we started with. Okay, so our mirror symmetry then looks something like this. We have YD mapping down to B, and then we have all these structures. And okay, so I'm going to write something that I'm not going to explain at all. I don't think anyone does for some reason. Okay, let me just write it. So Y, B, B, and then I have all these mirror structures. B dual, I omega dual, and holomorphic volume form dual. Okay, so these parts are exactly the same. I'm just equipping it with different kinds of structures. So this is my J, omega, and capital omega as before. And this B is what's called a B field. So if you want the real SYZ picture, you have to actually have this B field. And we generally try to just not talk about it because I don't know why exactly. People are lazy, maybe. But we're going to be in a case today in this Hacking Keating theorem where there's a justification why this B field shouldn't be there. Okay, and we know that kind of now? Okay, so I know that now I can match the symplectic invariance of this side with the holomorphic invariance of this side and vice versa. So I have symplectic, complex, or holomorphic, and symplectic, complex, and these two sides should match with each other. Okay, and as I mentioned the last time, kind of something that's a feature of this very strong mirror symmetry that you can do this interchange can also be seen as, okay, maybe I just want to understand this implication. And then you can drop out some of the structures. They don't contribute. Okay, so what I want to do now is to analyze both of these implications very briefly, say that one of them is actually much simpler than the other, which corresponds to the Hacking Keating theorem. And the other one is actually much less developed, even though many more people thought about that direction. It's not. The right-hand side is not a log Calabi-Yau. It's a completely different. You don't know what kind of complex manifold you have. It's not even going to be, it's going to be Stein at most. Well, it doesn't exist, but if it did exist, you expect it to be at most Stein, huh? Sorry?
Y minus D, so we have like that left extreme. So for them, Y minus D.
So these are both the same vibration. Same, yes. Just as I said, only in dimension 2 with special kind of singularities which happen in SYZ vibrations, you can do this. Huh? I didn't say anything about integral affine structure. B is just a smooth manifold here. Yes, yes, that's true. But okay, so what they make is they make this bold face, so everyone's happy. You make this bold face. Okay. Okay, so now I explain.
Now, example, he was a polygon or
So it's in one. So polygon, a special choice of coordinate system, something like that. Okay, and it's going to be something that's diffeomorphic to a disk. But yes, okay. So some remark is that, as we already discussed, Gross, Hacking, Keating, and also Gross-Siebert program, they can start on the left and almost produce the right. And almost is because of this issue with the formal family versus actual family and convergence. It's complicated issues, but more on this in other talks. Okay, so one thing that we know, again, I'm going to kind of keep telling you things that SYZ suggests without really explaining it. One thing, so as I said, like this structure, J check, and this omega check, and even sometimes this B field, it's actually very difficult to describe. So all this scattering diagram stuff that we heard last lecture, it goes into defining this J hat, J check. Okay, so those are very difficult, but one part of the structure is easy. This omega check is easy. Okay, so we have omega check is just equal to the imaginary part of our holomorphic volume form on the left. Okay, so this part we understand. And this, even though it's kind of a weird symplectic form, for example, if you consider this y minus t with its standard complex structure, this is not a Kähler form for that. This is not compatible with that almost complex structure, but it's actually a very nice symplectic form. Symplectic form, for example, on let's say a toric model C star squared embedded into Y, we have exactly C. So I know that C star squared is diffeomorphic to the cotangent bundle of T2. So it's just cotangent bundle of T2 is, so this is just the cotangent bundle of S1 cross cotangent bundle of S1. And the cotangent bundle of S1 is a cylinder, which is also C star. So this guy and that guy are diffeomorphic, but we also know that this cotangent bundle admits a canonical symplectic structure. And this imaginary part of holomorphic volume form gives you that standard structure. Okay. But not true, for example, for Kähler structures. Okay, so the actual structures which are Kähler for Y, this is not true. Okay, so now there are two expectations. Now, two expectations. Okay, one. It's y. I keep doing this. So the whole complex, using the complex structure of the left-hand side, I should be able to obtain something about the symplectic structure on the right-hand side. And so that symplectic structure is this omega check, which I told you is the imaginary part, and something about the B field, which I want to keep implicit. Okay, so this should correspond to y mod d, and maybe I start putting an underline here because I'm really not using the complex structure that's coming from this being a Looijenga pair. Okay, and this is imaginary part of omega plus something about the B field. Okay, so this B side, complex side, should correspond to the symplectic side of the other, in this SYZ mirror symmetry. And then there's another one. So this is the one that I'm going to focus on. And this is the one that Hacking Keating theorem is about. Okay, but let's momentarily also look at the other one. So you can also consider y minus d, omega restricted to y minus d. And this is supposed to be mirror to y minus d underline. So we don't forget about the complex structure, but we have some other complex structure here now.
So this omega is one of that.
Not necessarily, but we're going to work. So the Hacking Keating theorem is going to further specialize. Yeah, this definitely is not exact, but that's also not necessarily exact. So nothing is necessarily exact at this point. Yes. So the only case where this becomes exact is when D is ample. And then you can use this affine symplectic structure, and then you're in good shape. And then this side is actually a good, very good place to work in. So I claim that this is more tricky. So except the positive case, where this is affine, actually the left-hand side, this guy, this here, left-hand side, is not a good symplectic manifold to even work with. It's an incomplete symplectic manifold. You know, to define symplectic invariance, you need your manifold to behave well at infinity in some way. And these manifolds, at first sight, they just don't satisfy these conditions. So it's difficult to even kind of make sense of what are the invariants that you're considering here, because you may not be able to define them, except the positive case. And so this side is more complicated, but this side is also more complicated because, as I said, this J check, you don't know anything about that from just SYZ, some complex structure. And in examples, you see that this is more like a Stein manifold. Okay, if anything, it's something like you take a cusp singularity, you smooth it, and then you take some ball which kind of encapsulates everything, and you chop off the infinity and so on. Okay, so it's not something like an affine variety or a projective variety.
The toric case comes under the positive. The toric case is the positive.
Toric case is the positive case. Yes. Okay. Okay, so now I want to say just a little bit about the Lagrangian fibrations. So, and then move on to the discussion of Hacking Keating theorem. So the omega restricted to y minus d kind of symplectic structures. Structures admit Lagrangian torus fibrations with base looking something like this. So you take the moment polytope and you chop off some of these, you chop off some triangles from some of these sides, or something maybe a little bit more than, I think something like this. And then at the tips of these triangles, there are singular points. Okay, so this is Philip's picture. But the other one, the imaginary part of omega 1, it actually, so now there's something that we didn't fully explain, no one ever did. There is some integral affine structure on this manifold in the base. And this picture is kind of drawn with respect to an integral affine structure, integral affine coordinates, like particular coordinates that are special here. So it's not some random picture. And here there is a similar picture. There's a similar special set of coordinates. And there, I actually have a picture that looks kind of like this. Okay, so that one is polygon with this triangles removed, whereas this one is over an entire plane. Okay, just a remark for. Oh, but again, this one is nicer. So here, the preimage of these this edges is the divisor. So you should think that these are not there if we're thinking about the complement. Okay. So what I want to do is I want to focus now on this expectation. Okay, so let's introduce some notation. Okay, so let's call U this complement, the suffering ends. So now I introduce a notation for this complement. And I had referred to this class of the fiber of an SYZ fibration. Let me now define that carefully. So U comma Z. And is obtained by looking at the crossing torus near a maximal, a node, I should say it like this, near a node of D. Okay, so I have this D, here I have something like this. And if I just focus on here, I have this node. And here, locally, this just looks like C inside C2. Okay? And here I can define a torus by taking the product of the unit circle in one copy of C and the unit circle in the other copy of C. This is called the crossing torus. And this has a homology class. Okay, so that gamma is that homology class. And you might say, maybe it depends on kind of which crossing I choose, but it doesn't, because you can characterize this class as gamma generates the kernel of H2 UZ to H2 YZ, I think. It's the class that dies in H2 when you compactify. Okay, so now let me introduce a couple more pieces of notation. So I have this abelian group Q, which is just H2 U Z modulo this class of the fiber. Okay, and I can define a group homomorphism phi from Q to C star by taking an alpha and looking at the exponential of the period So maybe there's also 2 pi I integral alpha tilde omega. Okay, so alpha tilde is just, so I have an element of alpha in this quotient. I just lift it in any way I want. And the result doesn't depend on this lift. So that's what alpha tilde is. And the theorem, the reason why I'm saying something about this at all, is that the map phi, this is some kind of period map. So we know that, period maps often kind of describe. So if you have a moduli space of complex structures, by looking at this kind of integrals over integral chains, integral used in 2 different ways, you can actually distinguish different points on these moduli spaces. Okay, so the map phi determines the log Calabi-Yau pair in its deformation class. And remember that we actually have a kind of a good description of this deformation class of a log Calabi-Yau. You choose a toric model, and it's given by blowing up certain points. And if you vary the positions of those certain points, then you get the entire moduli, actually. That's the deformation. That's everything that's deformation equivalent to a given log Calabi-Yau pair. And if you just look at these periods, you can distinguish it within that family. Okay, so deformation here, think of as varying the blow-up points. Okay, so this is a theorem of gross Hacking Keating, I think. Okay, and now, well, the theorem that I'm going to write, which is about this, is actually going to be a special case where I'm only going to consider a special element of each deformation class and have a statement for that. Let's keep that statement there for a moment, maybe. So definition. Okay, so U has distinguished complex structure if phi is the trivial map, the trivial homomorphism. Okay, so you look at all these periods, and what they're supposed to be is, so this one's supposed to be always equal to 1. So these periods are always supposed to be integral. Okay. And only then I will have a mirror symmetry statement, like this theorem that I will talk about only holds then. So now, let me say a remark. Okay, so remark. Now I'm going to kind of go back to SYZ intuition a little bit, because I want to say something about what the implications are of this complex structure here being distinguished for the mirror. Okay. So SYZ intuition suggests that this condition is mirror to B field vanishing and imaginary part of omega being exact. Well, actually, the second part is trivial to see, because these things only should be integral. So their imaginary parts should vanish. So it just actually vanishes on the entire H2. Okay, so it's exact. So this is the implication. In fact, it's not too difficult to see. This is not exactly part of the SYZ intuition, but it's further work to see that U underline imaginary theta is symplectomorphic to M d theta, where M theta is Weinstein manifold. And in fact, we can explicitly describe which Weinstein manifold this is looking at a toric model. And Doğancan will explain, I think, this Weinstein manifold. It's obtained by attaching stuff to the cotangent bundle of the torus. Okay, so now let's so theorem. Hacking Keating, it's from like 2020. In a derived sense, the wrapped Fukaya category of this Weinstein manifold is symplectomorphic to category of coherent sheaves on U with its standard J, right? Okay, so now if you go and look at this paper, then you will see a very different statement. So in particular, this side is constructed in a completely different way so that the proof works best. It's constructed using a Lefschetz vibration, okay? And then it's proved that actually that Lefschetz vibration is equivalent to what I'm telling you here. Okay, so the proof here is kind of, I would say, very indirect, and it uses Lefschetz techniques. And it uses a lot of previous work. My advisor and Elsa Keating is also a student of my advisor, and Paul Hacking is kind of an expert on. Oh, sorry. Yes, no, it's okay. So you get the statement from something like this. Let me just write that. Book. Let's make this W. Oh, Y. So you first prove that some category associated to a Lefschetz vibration is isomorphic to the category of coherent sheaves on the compactification. And you prove some other statement about the fiber of this Lefschetz vibration and some kind of category associated to the divisor. And then you do a categorical localization to get from this statement to this statement. So it's very indirect, and it's not something that you would have really imagined. Like to construct kind of the Lefschetz vibration that you need to use to get this statement to be true, it's kind of very difficult to just guess that. But I'll say something about why they guessed it.
Do we need to take the right category from Fukaya?
Okay, so I don't want to get into this discussion because we didn't define anything. So, but it's an actual statement. That's my point. Like, this is a well-defined category. It was defined in Doğancan's talk, kind of. And this is a well-defined category, and they are really equivalent in the only possible sense. And it's a proved theorem. So I motivated it through a bunch of intuition, but in the end, at the end of the day, you get an actual theorem. So something that I want to remark is I think there's this kind of proof by Hacking and Keating, which relies on their experience about this kind of both sides of this, but I think probably sheaf theoretic proofs exist, and they're probably also easier. Great. So proof might be easier using sheaf theory, microsheaf theory. Okay, so now I want to just end by kind of telling you a little bit about the history of this theorem from my point of view. So how this theorem came about. So the history of the result. Okay, so independently from the GHKS story, so what we've been discussing, there was a conjecture by Takahashi okay, and this conjecture said the following thing. So let TPQR be the singularity at the origin of the following polynomial of C3 to C. So it's going to be a family depending on these positive integers PQR. In fact, they're more than positive. They have some, they're bigger than 3 or 4. Or I think their inverses, the sum of their inverses should be bigger than 1. Okay. Something like this. Smaller than 1. 1 is 1, right? Okay. Yes. And so the singularity is the polynomial is this. The R plus XYZ. Okay. So something that's well known about this singularity is that this is a cusp singularity. At the origin, this is a cusp singularity, and it's actually these are all the cusp singularities that happen as hypersurface cusp singularities. Okay, so the ones that can be written just using one polynomial in C3.
These are the ones whose dual has length 3.
Yeah. Yep. And those the singularities, those are called like triangle singularities, right? They also have a name.
I think if the XYZ goes to 0, then that's called a triangle singularity. And then the 3 lines meet.
Okay, let's so now. So now I will attribute this to my advisor. So there was a definition of some category, directed Fukaya category associated to such a singularity. Okay, it's some kind of category. It's an A infinity category. Okay. So now we have this singularity, we have this category. And Takahashi made a conjecture about what this category is. The conjecture was that the Fukaya category of TPQR should be isomorphic to P1 PQR. So this P1 PQR is an orbifold projective line. Okay, so this is an orbifold projective line with like 3 points with non-trivial isotropy of order P, Q, and R. Okay. And this conjecture, I believe he made this conjecture by looking at what's called the K0 and the Euler pairing on these categories. Okay, so there's here, this is kind of what's called a categorification of a certain kind of intersection pairing on the smooth fibers of the singularity. Okay, and you can compute that. It was computed, and they also knew this one, and they matched. So I think it was reasonable to say that the categories will match too, and this is true.